Between 25,000 and about 300,000 years ago, much of Britain was covered several times by thick ice sheets. And this ice eroded mountainous areas to produce rugged topography and broad U-shaped valleys. When the ice melted, it left behind stuff like this. There's a huge range of particle sizes here, from this kind of material, 10 or even 30 centimeters across, right down to this fairly sticky clay, which when we look at it under microscope, we find that it's only a few thousandths of a millimeter across. So we have a huge range of grain size. Similar deposits to this one are forming today, where ice sheets are melting, both at the ends of glaciers and underneath them. The pebbles and boulders fall into the ice from surrounding valley sides, and the fine clay is produced by the ice and included rock material, moving over rocks and grinding them up to a rock flour. When the ice melts, all this material is dumped, so there's little chance for running water to sort it into separate deposits of pebbles, sand or clay. So the end result is this material, which is called boulder clay, and much of Britain is mantled with it, especially around mountainous regions and in areas of eastern lowland Britain, such as County Durham, where we are now. Well, if we could find fossil equivalents of this boulder clay, hundreds of millions of years old, with boulders floating in clay, then they'd give us some indication of the kind of climate that might have been in existence at that time, whether the area was glaciated or not. Well, in Scotland, we do find such rocks. They're about 700 million years old, and they look remarkably similar to the boulder clay we've just been looking at, except that what was once originally clay has now been forged into hard rock by heat and pressure. So this is evidence that Britain experienced a cold ice age type of climate 700 million years ago. Well, you may be thinking that the present-day climate in Britain isn't much different from an ice age, and indeed we're probably in just a slightly warmer period between successive periods of glaciation. But there have been times when Britain has had a much hotter climate. I'm standing on a coal seam that's about 300 million years old. So that junction between the boulder clay and the coal seam represents a huge time gap. There are two coal seams in this pit, separated by layers of mud and fine sand that are now shale and sandstone. And these rocks contain remains of the plant material that makes up the coal. Let's have a look. Well, experience made me think this was the kind of rock that we'd find fossils in, and I've been pretty lucky. There's a rather nice little fern leaf, looking a bit like bracken. And when I look around over this heap of rock, there's quite a few fossils. Look at this block. Maybe this might show something. Yes, another bracken-looking thing and some kind of plant stem. And over here, a pretty large piece of wood, with the woody material now turned into coal. So it looks as though all this plant material has been washed in, it's been broken up. But there are rare occasions when one can actually find complete plant fossils. Incredible, aren't they? This is a glimpse into an environment of the past, a past world some 300 million years ago. And trees like these probably grew to a height of about 100 feet. And between them would have been growing a dense thicket of vegetation which would eventually form the kind of plant fossils we found in the pit in Durham. Well, these trees are preserved in a park in Glasgow, actually appropriately in a glass house, because the kind of environment these grew in was probably very hot and swampy. Look at these roots, a very shallow system of roots, much like those we see in trees growing in swampy conditions today. And the kind of vegetation, the kind of plant fossils we find also indicate hot, swampy conditions. So we can be pretty certain that the coal forests that formed Britain's huge deposits of coal grew in hot, equatorial conditions. This probably means that the country was situated on the equator 300 million years ago. At the present time, equatorial rainforest areas are flanked to the north and south by hot, dry regions. And in parts of these occur vast sand deserts. Sand dunes like these are another kind of rock in the making. The sand grains they're made of have a very uniform grain size, around 1 millimeter in diameter, and the sand grains are extremely well rounded. Well, these are British desert sands, but they're 270 million years old. And one clue to their origin is that crisscross pattern. Well, here's one small part of that crisscross pattern, and the individual layers of sand are sloping off from right to left. Well, imagine this line as the surface of a sand dune, the downwind or leeward surface of the sand dune. And let's imagine that the wind was blowing in this direction, from right to left. Now the wind's going to be carrying in sand, and the wind velocity will drop in this area, so the sand will be deposited. And so layer upon layer of sand will build up. And there we can see yet another layer that's been etched out by the wind. So the layering in this sand then is a direct indication of the wind direction which actually brought these sands in. So if we can measure the inclination, we can get some idea of the wind direction. Now the problem is that these dunes would have had rather curved crests, so the inclination on the layering would vary a bit, so we'd have to take a lot of readings, but this can be done, it's been done for this quarry, and the direction we get is west-southwest, so we can say that is a paleo wind direction for these sands. And lots of measurements have been taken in sands of the same age all over the country, and they all come out with roughly the same direction. That is west-southwest, which is indicating a wind blowing from the north-northeast. And that's just the same as in the present-day Sahara. Well, another clue which suggests a desert origin for these sands is the shape and size of this crisscross pattern. They're quite large, they're up to a couple of meters thick in places, and they have this characteristic curved pattern. And when we look very closely at these sands, we find they also have a characteristic shape and size. Along an individual layer, the size of the grains is pretty well the same, and they're extremely well rounded, just like the kind of sands we find in modern deserts. If we look at the top surface of the sands, where they're overlain by younger rocks, there's an undulating surface. And this is typical of the kind of topography we get in a sand desert today. So we've evidenced that Britain's experienced extremes of climate. 700 million years ago, we had cold polar conditions. 300 million years ago, we had hot, wet, equatorial forests. And 30 million years later, at 270 million years ago, dry, hot deserts. And today, we've fairly cold, temperate conditions. So there's evidence that Britain's moved successively northwards through geological time, perhaps even starting at the South Pole. Even during ice ages, the order of climatic belts between pole and equator stays the same. But as the extent of the polar ice cap expands, the intermediate climatic belts contract, and vice versa. And these small shifts in the climatic belts are not enough to account for the differences in the rocks we were looking at earlier. But perhaps the best climatic confirmation of the drift hypothesis comes from the southern hemisphere. Look at the distribution of deposits formed from ice sheets 250 million years ago. If the continents hadn't drifted, the ice would have extended from the South Pole to the equator. But if we put the continents back together again, then the ice sheet assumes a much more reasonable size. But let's look again at the polar wandering curves for Europe and North America. There's a good fit between 200 and 400 million years ago. But beyond 400 million years, the curves diverge. Does this mean that the two continents were separate at this time? Well, these fossils are important clues. They're trilobites, an extinct group of animals related to insects, lobsters and the like. And many of them look like overgrown woodlice with segmented bodies and shield-like heads. They burrowed or crawled on the sea bottom or swam just above it. Examples like this one existed in northwest Scotland, and ones like this in Wales. And they're not found together anywhere, even though the two areas today are close together and shallow sea bottom organisms could easily migrate between them. But remarkably, similar fossils are found in Newfoundland, 5,000 kilometres away. So this suggests a former link between Newfoundland and Britain via shallow seas, not a deep ocean like the Atlantic. Well, if we close the Atlantic, we can see that this is precisely the case. But the other remarkable thing is that the trilobites in northern Newfoundland are similar to those in Scotland, while those in the south of Newfoundland are similar to those in Wales. So we can draw in a dividing line between the two groups of fossil trilobites. Some kind of barrier along this line must have kept the two groups apart, either land or deep ocean. Evidence from the rock sequences suggests that an ocean separated the two continents, with Scotland being a part of North America and South Newfoundland a part of Europe. This ocean is often referred to as the Proto-Atlantic. About 500 million years ago, this ocean was probably shrinking as the two continents moved together and eventually collided, throwing up a mountain chain that stretches from Greenland and Scandinavia into West Africa and Eastern America. The fact that this mountain belt aged about 400 to 450 million years, though present now on widely separated continents, can be merged into one if all the continents are fitted together, is yet more evidence in favour of drift. So we've examined 4 pieces of evidence favouring drift: the paleoclimatic evidence for latitudinal drift, the paleomagnetic evidence from polar wandering curves, the fossil links between distant continents, and the fact that widely separated bits of mountain belts of the same age can be fitted back together to form a single belt. Compelling evidence confirming the drift hypothesis comes from the oceans. Magnetic anomaly patterns show that seafloor spreading occurs along ocean ridges. The ridges are offset by transform faults, and these extend landwards as fracture zones. We can use these fracture zones to reconstruct the movement of the continents. Well, let's look a little closer at the geometry of the mid-Atlantic ridge and its associated fracture zones. Well, to do that, I'm going to play around with a number of hoops of different diameters, such as this one. Now, this one has the same diameter as that of this model globe of the Earth. So if I fit it over the Earth in this direction, it should coincide with the equator. There, it's a pretty good fit. So the circle then, the hoop, has the same diameter as that of the Earth. That means that it's a great circle. Now, great circles are also lines of longitude, and so they should pass through the pole and be at right angles to the equator. And I can move this hoop around to successive positions, rotating it around the pole to reproduce successive lines of longitude. So lines of longitude then are great circles. Now this hoop is much smaller, and if I again place it over the globe, parallel to the equator, it's now representing a line of latitude on the Earth's surface. So it is a small circle with a diameter less than that of the Earth. Now, what have all these great and small circles to do with the geometry of the mid-Atlantic ridge? Well, let's see if we can fit this particular hoop to one of the fracture zones. I'm going to try to see if I can fit it to the Romanche fracture zone, this very pronounced one in the equatorial region of the Atlantic. Well, we get a pretty good fit. It seems that the Romanche fracture zone is coincident with a small circle, but this small circle is not parallel to the equator. Now, that isn't a unique case. I've got two more hoops here, and I can do the same kind of exercise. This one has still smaller a diameter. Well, this one seems to fit this fracture zone here, which has quite a large displacement. That's the Vima fracture zone. And here's a hoop with a smaller diameter still. That fits this fracture zone here, the Kane fracture zone. So it seems as though this relationship between small circles and the trend of these arcuate fracture zones in the Atlantic Ocean is not a coincidence. They're all lining up parallel to each other along these small circles. Well, plainly, these small circles are not arranged concentrically around the geographic pole. It looks as though they're arranged around another pole somewhere in here. Well, to find out the position of that pole, let's plot in a great circle at right angles to one of these fracture zones. So I'll take two of the smaller ones off and go back to using this great circle again. So what I'll do is put it on the globe at right angles to the small circle coincident with the Romanche fracture zone. Now, can you notice any relationship between the mid-Atlantic ridge in the vicinity of the Romanche fracture zone and that great circle? Well, the ridge segments are trending parallel to that great circle. So it seems we have another nice relationship. Segments of the mid-Atlantic ridge are trending parallel to great circles. Well, let's plot some more great circles at right angles to the fracture zones in the mid-Atlantic ridge. Well, all the great circles intersect this area. So this locates a pole. But what kind of pole is it? Well, it's a pole of spreading about which South America rotated away from Africa. And we can actually locate the fracture zones in distance from this pole by quoting an angular distance. For instance, the Romanche fracture zone is about 65 degrees from the pole of spreading. This pole is also the pole of opening for the South Atlantic, where two continents, South America and Africa, have moved apart. And you can see that the rate of spreading varies from 0 at the pole and increases away from it. In reality, this is not a gradual increase. It jumps in amount across the transformed faults. So the movement of continents can be described using poles of opening and actual angular distance of opening. Now, the Earth's crust is divided into lithospheric plates, which include both continental and oceanic crust in their upper parts. Now, most of the plates are already on this globe. This is the Pacific plate. It's largely oceanic crust. And here is the Eurasian plate, largely continental crust. And here's a plate that I've yet to put on this globe, so you can see underneath is the outline of Africa, roughly marking the continental crust, and to the west, half of the Atlantic Ocean. And here is the African plate. Now, the boundaries of these plates on the globe are, of course, marked by seismic activity. In the case of the Atlantic Ocean, running down the mid-Atlantic ridge. Well, these two plates are increasing in size due to the generation of new oceanic crust along the mid-oceanic ridge. So we call this boundary between the two plates a constructive plate margin. But if these plates are growing in size, somewhere material must be being destroyed. And this happens where two adjacent plates of different densities meet, such as along the west side of the South American continental plate, where, here it is, the western side of the South American plate, where it meets the Nazca plate. And this is a site of a deep ocean trench. The continental plate has an average density of 2,700 kilograms per cubic meter, whereas the density of the oceanic crust is about 3,000. But when the two plates meet like this small density difference causes the ocean floor to be driven down beneath the advancing continental plate along an inclined zone of seismic activity, which is generally referred to as the Benioff zone. And as it pushes deeper into the Earth, part of this cold oceanic slab will start to melt, and the rock liquid produced will rise through the overlying continental mass to give rise to volcanic activity. And we call this type of plate margin a destructive margin. But what happens if there is no density difference? Well, there are two possibilities: collision between two oceanic plates or collision between two continental plates. Let's take an ocean-ocean boundary first. To start with, two adjacent segments of ocean crust meet and are driven down steeply into the mantle, completing the downgoing limb of a convection cell, much as that envisaged by Professor Harry Hess. Such limbs are never quite vertical, but lean slightly, so that one segment of ocean lithosphere overrides the other. Now, the lithosphere, which is diving into the mantle, heats up, and the upper parts of it, formerly ocean crust, start to melt. And the magma produced in this way, being lighter than its surroundings, starts to rise and eventually produces a volcanic eruption. Chains of volcanic islands produced in this way are known as island arcs, and there are some good examples in the Western Pacific. The Japanese islands, the Marianas, the Philippines, and the Tonga Islands all form chains of volcanic island arcs. And these occur where the Pacific Ocean crust is being subducted. Now, looking at the Pacific Ocean as a whole, we find that subduction is occurring today on both the east and west sides. And the result is that the ocean is shrinking, because Australasia and America are both overriding the Pacific Ocean crust from opposite directions. The subduction rates are therefore much faster than the rate of lithospheric generation at the ocean ridges. So what will happen as the Pacific shrinks away? Well, this brings us to continent-continent collisions, where again two masses of like density meet. In this case, both are less dense than the underlying mantle, and so the result is that neither can be subducted. They are forced to collide head-on, and the crust thickens to more than twice the normal amount. This is just what happened when India moved northwards to collide with Asia, producing the Himalayan mountain chain. Seismic evidence has shown that the crust in this area is 90 kilometers thick in places. Compare this with the normal thickness of around 35 kilometers. So we have a continual system of formation of new ocean floor at ocean ridges and subduction of oceanic crust beneath ocean trenches. Let's close by having a look at a constructive plate margin in Iceland.